So if you would please go to like 5. Yeah. On this GitHub repo you can get slides and also follow the code which is in the repo, which is called today's date 23/12/09-parallelization. Inside it you can follow the scripts which I'll be presenting today. Okay, so let's start. The contents for today's is really just the surface of what parallelization and parallel processing is really so today will be like just introductory level for basics for that everybody can try on their laptops, and we'll use the API which is built in Python, which is called multiprocessing. So we'll start with explaining why multiprocessing can be useful for software engineers, and also today we'll cover the most popular and the most standard way to use multiprocessing in Python, and we will show how to share memory between different processes, and we'll go into some further details a little bit, and then we'll show some applications how it can be used in machine learning, because our session is related mostly to machine learning related applications. So, and there are a few reasons why parallel processing or making a few threads can be useful in general. First one is increased performance. We can get our results much more quicker if we would do it in a single thread on a single process. Secondly, from the hardware concern, we can use our resources more efficiently. Let's say we have very powerful compute, but we are not utilizing fully what we can. So it would be more efficient if we would use some technique to use the full capacity of our code. And also another reason can be scalability. For example, if you adjust your code in processed way, then with extension of the new hardware, you can basically spread processes or scale your processes so that your overall result will be even faster. So it gives you kind of flexibility and scalability in that terms. And one of the important ones as well, it can help to solve complex problems. For example, especially in the scientific computing or like AI, then the computation processes and some functions can be really heavy, and if you split into the single more smaller level sub-functions or sub-processes, it can help you to build up to the final result and in a more efficient way. So it kind of opens the new capacity for the new problems. Let's start with some basics. We start some basics about what is parallelization and how it is different from concurrency, if some of you may have heard. Like some time ago, I'm not sure if I was coding that time, but there were computers on a single core processors, and for example, the maximum you couldn't really parallelize much of really make simultaneous operations at the same time. At that time, okay. So if you wanted to have a few threads kind of simultaneously, then there were mechanisms to switch between different tasks and help you to achieve several tasks in a more efficient way. But the true parallelization comes when you truly can split task from one core, let's say, to another core, and then every task will truly happen at the same time without switching. In that terms, one.
Always have a backup.
that terms, we can say that in parallel processing, the tasks happen like more independently compared to like concurrent version of it. If anybody have questions on the way, feel free to like raise your hands. We can discuss. And like one more disclaimer that I wanted to say but forgot to mention is that I'm also not the expert about this topic in general, but I have interest and I have a little bit of experience related to these kind of things. So if you feel that like you want to pinpoint some detail, feel free about it, and we can discuss and check later as well. Another thing, like concurrency mostly happens on a single core, which makes the switching possible. So in that case, concurrency is mostly related to threads, to more like element code threads, and the parallelization is more related to the like processing. So what's the difference between thread and process like as a whole? The biggest one is that threads share the memory space with other threads, and you can pass you can share the memory with another thread if you want to like update let's say some variable from one thread to another thread, and this kind of communication is easier within the same process between threads. Whereas like one process is isolated from the other one, like we don't have the access from one memory to another one, but there are like special mechanisms how they can communicate like externally. And one more thing to say is that like threads have lower overhead because of this sharing of memory, how they can communicate, and in that case process more like have high overhead. It's more cost takes more cost to create one and to close one as well. And yeah, that's kind of one of the main differences between threads and processes. And if you've experimented with threads and processes in Python, the general like syntax can be similar, pretty much similar. For example, on the left side, on the left column, there is like threading API, threading module in Python, which helps you to create one thread. And on the right column, there is a process, like multiprocessing module, and how you can create a simple process. Actually, on the surface, it's not really different. Like if we write the actual code, but internally they're different. For example, how about making a small experiment and then seeing if we increase number of threads and increase the number of processes, how much they can affect, like which one is better, getting more threads or getting more processes. I'm saying about Python, so like this kind of content is only about Python based, not related to any other language, so please keep in mind. So if we make a simple like code which to get the square of numbers from 1 to 1 million, and like scale it to scale the number of processes on one hand, and on the other hand try to scale the number of threads. And here and we'll also try to compare which one is better for us. For example, in this graph shows that the blue one, if we kind of exponentially try to increase the number of threads from 1 to 32, which was the kind of capacity of my PC, up to 32. So you can see that with the growth of number of processes, the elapsed time for a specific function gets less and less, which means our overall utilization like much quicker to finish, compared if we just increase the number of threads like from 1 to 32. It's not really worse. Like sometimes it can be even go a little bit up. So is there any idea why can this happen in Python? Anyone have any guess why it might happen? Even though we scale the number of threads, the output, like final result, is not really efficient. Any Beach, of course, knows. How about other guys? Like, anybody has idea? Okay, no idea. And yep.
I think Python is basically single thread task bank.
Yeah, this goes to like correct direction. So Python, when it was designed, was originally kind of planned for. There is an okay. Let's just say it's about GIL, like GIL. It's a global interpreter lock, which kind of blocks. It's not really blocking, but it's not how to say as much. Like, it doesn't matter whether like one thread or multiple threads, your Python interpreter will still like utilize global interpreter lock, which kind of locks one thread at a time for the interpreter case. So if it makes sense, like more like the if we show illustration about it. So let's say we have like thread 1, thread 2, thread 3, thread 4 in Python, and then there is like interpreter lock, and then only one thread at a time can be processed by your Python interpreter. That's kind of like the drawback of the language compared to other languages in programming. So that's why if we go back to our graph, we can see that no matter like we have one thread or two threads, 32 threads, still the final like elapsed time remains almost same compared to scaling the number of processes. So another thing to note, like from this graph, from this experiment, is like if we just have originally before our experiment, like would we think that if we increase number of processes, our time will decrease in a linear way, for example, but when we actually did it, like when we actually code, we can see that it's not really decreasing in a linear fashion. Like even though we exponentially increase 2, 4, 8, 16, so the graph is kind of, so it means at some point there is it starts to stagnate, to decrease, and then stagnate at some point. So why is that? Why it can happen? Any idea? No. Yeah. So yeah, it's a bit difficult topic actually for me also. Like I couldn't really understand, but there is if we go to the theoretical part of it, it's defined by the which is called Amdahl's law. There is a simple formula for it, which kind of explains why your speed up isn't like in a linear fashion as you would expect with increasing the number of processes. So like in this equation, S basically means the speed up, the overall speed up like of your system, and then in the denominator part, there are like two variables which you can change and like make experiment as well, like how they affect one to another. P is like fraction of the algorithm which can really be parallelized, because not every piece of code can be parallelized. So we should also take this into consideration, and the number of CPU threads. Let's say here I also made the graph yesterday to show, for example, how if we try to, based on this equation, if we, let's say, assume our 50% of our code can be parallelized from 50, and then like 75, 90%, 95%, what is the maximum speed up I can gain from my processors, right? And if we can check this graph, you can see that for example, in my PC with the 32 processors, the maximum I can get at 95% parallelized, 95% parallelizable code is about like 13 to 14x, even though my number of processors is 32, right? So this is the important thing here is just to know that there is a limitation. There is a limitation, and this limitation is basically also related to the how much portion of your code can be really parallelized.
I have a question.
Yeah.
When you say processors, do you mean CPU cores?
CPU cores, I mean processors. Like in my case, for example, I also actually was wondering yesterday about MISI, like it made me a bit confused. So from the here. If we check, for example, if your machine is Windows, in the task manager, you can see what is the number of cores and what is the number of logical processors. In our case, for example, in my machine, like I had a 16-core machine, but when we check down, there is also a line number of logical processors is 32. So we should refer to that number of processors. Make sense? Does it make sense? Yeah. So yeah, like this n basically in the equation is the number of processors, and this graph is also based on the number of processors. Yeah.
If you have one CPU core, can it only handle one process?
One CPU core can have. Not necessarily. Not like one course, like here, for example, in my setup, like one core can two processes per one core, like that. Two logical processors per one core. So yeah.
Can I help?
Yeah.
So the processor is like the physical component on your computer. It can have multiple cores. So I think in this case, logical processors. Wait, no, what the hell? It's backwards. I don't know, it's confusing.
Yeah.
You usually have more possible compute for threads than you have physical processors. So in this case, he has 16 physical things in his computer, but he can run 32 threads.
Okay, so thread is the same as processor.
A processor can run.
Yeah, like here.
A processor is
Type
what
of.
runs a
You
thread.
mean about this one? Sorry,
You have
yeah.
threads, processor, and CPU cores. I'm mixing them up.
You okay? CPU.
CPU core.
Cores.
Yeah,
Okay, CPU core.
cores, and processors
Mm-hmm.
and threads.
So you have some number of
okay,
physical
okay.
CPU cores,
Okay.
Yes.
and they have some number of logical processors.
Okay.
Now, one CPU core often can run two logical processors.
Two threads.
Two logical
And the
processors.
one processor runs one thread.
Okay.
Yes.
Yeah, like in every process, we can design such way that like one process can hold one thread, like that. So like to one process, we can also put multiple threads too. So how to say? It doesn't like
But it's not. It's not. If one processor is doing multiple threads, it's doing them like this kind of thing, not like this. Sorry. Keep going. Forget me.
Yeah, keep going.
Sorry. Let's discuss like after like, and yep. Any more questions about this slide? Actually, this is based on Windows. Like in Linux, there also might be some commands to know, like to check the configuration of your machine, how many cores you have, like how many like processors, processors as well, and you can also check on Linux-based machines for yourself. And let's. Like this is a little bit of basics. Of course, this is like the basics. There are a lot of things which is not covered, and like much more details if we go deeper. But for like introductory, should be enough to proceed further. The standard way to start the process in Python is to use multiprocessing module. And how can we actually run it is shown in this piece of code. This kind of script is also available in the GitHub repo, which I showed previously. You can, like, if you want to run and follow up on the same pace, you can put into your Python interpreter the same code. So here, like initially the main we should here note that everything which is inside here, like when we start Python code interpreter, it itself is already a main process. So, and if we want to start a new process within it, it means there is kind of another process. So another new process. So overall, for example, if we start two processes, process 1 and process 2, there will be three processes. Like one is main, and the main process starts like process 2 and process 3 here. And in the module we can put .start, and then we can check if it's running or not. Like function 1, like called worker 1, and function 2, worker 2, is basically just like any can be anything, but in our case I put this code to check whether this process is really started. How can we check it? So again, main started process 1 and process 2, and this should be running somewhere, because there is a while loop inside the function, and every 2 seconds it keeps looping, and we don't stop it anywhere from the code. So in Windows we can check it from Process Explorer. We can download it from the Google. Like if we type in the Google Process Explorer, it's free, and like after running our Python code, it shows our PID. Like from this code we can also print, if we check os.getPID, and we can see that the main process PID is 39,648, like process 1 is 480, and process 2 is 42236, and they like just keep running. And how do we actually capture, like how do we monitor if they're running? If you download Process Explorer and you open up, like there is a list of processes, and since I run it in Visual Studio Code, you can like expand, and find here that we can see like there are 3 processes overall. First one is main, and this main started the other 2, 480 and 42236, like the processes which were started from the Python. For Linux case can be a bit different, but like there is a command in the shell. You can type ps-a, and then it will show you like the list of processes here. And if you check the PID, it's the same PID that actually like tracks to our original Python script here. If you want to like run the code, you can run, and if you have questions, let's check. Like please raise your hand, and we can help you too. Any questions? No questions. Okay. Then the next thing is how to share memory. it's a bit tricky question because, as we mentioned here previously, every process is located within its own memory space. So how can we actually update, let's say, some variable in process 1 and like from process 2? Is it possible? And if it's possible, how do we do it? Let's check. The simplest case, like just without any knowledge of multiprocessing API, let's say we declare some kind of global variable. Okay, originally we have process 1 and process 2, and then we want to kind of append to the list from process 1 from the process 2. How do we do it? Is let's try like just making some simple global variable, and to that global variable try to like append some element from another process. And as a result, if you run this code on your machine, you will see that the global variable like didn't change. Like the result from the main process, if we check, it didn't change, and the list is still empty because it was declared originally is empty. Why is that? Is because of that reason that every process has its own memory space. So, but in order to update another process variable from one process to another, we can do the following. We can use the shared memory. Shared memory, it's also available like with several modules in within multiprocessing, which is like the simplest one is like value and array. Originally, we are creating some list, and we declare multiprocessing's array object of the size 3, so that it can hold 3 elements inside. And then we pass this object to the multiprocessing's process, right? And inside this, there is some kind of juggling inside this function to update. And then finally, if we check the result, we can see that that our variable has changed overall, like after running through another process, even though like they have their own memory space. Actually, how it's possible? Like how it's possible, because this process 1 has its own memory space and process 2 has its own memory space, is because there is some kind of shared memory that they agreed to contain, to communicate with, and process 1, like for example, can send and extract some data from it, and also process 2 can take and extract some data from the shared memory, and this is how they can communicate. But they cannot interact directly, so process 1 cannot directly like hack into the like memory space of process 2 and kind of change something within that memory space. And this is kind of the most trivial way how we can make memory sharing the memory between the processes. Any questions about it? Yeah, and the one thing here is here you can see that we created the process, we started the process, and we also put like p2.join, which is kind of some message saying that let's wait until this process is finished and not proceed with the like main process further until the new process is finished. This is how we can join the result from another process to the original one. Makes sense? Okay. Yeah, and here also, like after the result is finished, for example, we can also close our process to clean up the memory, but here I didn't do, just to explain the simplest case about sharing the memory. So originally we can also kind of close every process after joining. This is the trivial case where if you are coming from like C++ background, we kind of allocated array with number of elements of 3 and then put some elements within like each index, let's say. But how can we kind of interact with not arrays, but if we want to interact some various kind of data types, strings, integers, like lists, and so on and so on. For that case, Python's API has manager, which helps you to interact with different type of data types. Let's say like the simplest case is we want to have some dictionary, and within this dictionary we put different objects. Like one of them is string, another one can be integer, and like we want to change from like different processes the common kind of shared variable, the shared object between them. And manager can easily help you to do it. Here, like the way how we can interact is we say manager, we create a manager, and then we can create an object within this manager, let's say, and we can say, oh, this can be dictionary type, and within this dictionary we originally put some string Code Seoul and let's say some random number of members like 100, and then we want to change, we want to add new member from the other process, and for that case we just define our function which performs the actual operation, and then we pass our manager's dictionary object into it, and from here, from the like our function, we can just increment that object plus 1, and then we can also like put some string or like read other types of things from this variable. And then after manipulating, we after starting the process, we like waiting until the process is joined, like finished, and joining, and then we can continue with the main of the process. Like if we illustrate in the diagram, so there is a like parent process main, and then there is a child process, process 2, which we created newly from the code, and this is the manager's dictionary object within within a server process. Like I'll explain it, and then in this like this kind of server process, it contains some. Okay, so the manager is basically server process, which is a new process. It has like so manager is kind of high level object which automatically takes care for you to change the elements within shared memory, but shared memory not inside one process or another, but somewhere else without kind of making mess in the original processes. The way to do it is making another process, some kind of another not really independent process, and call it manager. In the terminology, it's called server process, and within server process, keeping that objects. So, and to that object, every other process can have access, and they can like read and write every operation without directly changing one to another thing. So, does it make sense? Yeah. Yeah. So here, like another thing to be careful about. For example, let's say we have like bunch of processes from like 1 to 1 million of processes. Actually, yeah, like and they have some kind of shared resource. like, let's say, some kind of manager's dictionary, which we created previously, and did it stop? Yeah. So, and every process want to have access, reading access as well as writing access to some kind of shared resource. And what happens if at the same time, simultaneously, one process tries to change the object and another process at the same time tries to change it as well? So there is no really like direct answer what will happen, because like there is unpredicted behavior which we cannot really predict, and it can be really different from time to time. But we want to have some kind of stability, and we also want to have access from every process to that kind of shared resource. How we can do it? Like this GIF is basically illustrates like explosion in simple terms. Like if like one process and second process try to access the same thing. In Python as well as in other languages, there is a thing which is called lock, and it's simply similar to like original lock in our like understanding, in human understanding. When let's say we have some kind of shared resource, and when one process tries to modify it, it locks for that period of time. So no other process can access it or can modify it as well. So, and while other process should wait, and then after finishing, like other process can also like change one by one what they wanted to do in the original case. If we check the code, it's really also like the basic example is here. Let's say we created some kind of shared resource. In our case, it's kind of integer, and its value is 0, and we want to increment the original integer like by 1, but from multiple processes at the same time. And then like we create some list of processes, and we start it one by one, and then we wait until every process is finished. Here, like the main difference here is that here we say with lock, and then we define what's the original behavior, what should be modified within this lock while it's locked. So in that case, then we can have our final shared counter the same behaviors that we originally planned to do. Any questions up to now? No? Okay, sure. So if there is no question, then we can proceed to the next slide. Pool. Now, next example. In our next example, we'll want to have a list. Thank you. Sorry. In our next example, we want to have some list, and we want to modify this list so that the final value is twice larger. Every element of that list is twice larger. If we do it in a serial way, like without using multiprocessing and without using several cores, here we create the list as usual, and then we iterate through the list and append every element, but at the same time we want to multiply and then put back to the like final result. Like for example, if you put 1, 2, 3 and single core, and like this will call the twice function, and twice function will return 2, 4, 6 correspondingly, right? So how can we do it like in multi-cores? Because we don't want to wait a lot of time if we have our powerful compute, and let's say like the simplest way to do can be creating a simple list as before, but then we make also a new process. But this process is not a simple process; it's kind of pool-based process, which automatically can help you to spread your job between the number of cores that you have in your setup. So if we just call the default in a default way, we make the new process, and then we map our list of elements to the functions that we want to have here, like multiplied by 2. And as a result, we will get 2, 4, 6. But the difference between this case and this case is that this one is serial and utilizes only one core, and here we can utilize like as many as our setup allows to do. And here, if we go back to our like diagram from here, this is how we can do. For example, we can create pool process like of number of processes saying 1, 2, 4 or 32, and then we can see like if we put 32 based pool, then like our time goes much faster as compared to 1. So here, for example, and your code can also like detect automatically which core can be. It kind of also automatically detects which core to utilize and which core not to utilize. If it needs only 3, it will utilize only 3, and some others will be kind of available for the next computational task. Any questions up to now? Thank you. Okay, if there is no question, like there is like a few things for this lecture. About hardware perspective, some of us, most of us, have heard about CPUs, GPUs, and different type of computers. But what is actually different, CPU and GPU, right? There was a famous video from Mythbusters. They demonstrate drawing a picture like if using the CPU, let's say CPU-based simulation and GPU-based simulation. Here, you can see that it's not doing a bad job; it's doing a good job actually, showing drawing the smiley face, and we can utilize multiple cores. It's pretty fast, if we would say. But on the other case, how GPU is different? So we cannot really compare, because CPU have just multiple cores, and GPU can have hundreds of cores. And if your operation is kind of atomic based, pretty simple, you can scale it to the number of cores in GPU and make use of your hardware much more efficiently. If there will be interest in the future about GPU-based processing, any kind of if you guys have any interest, we can maybe make similar session about GPU. But within today's lecture, we will only cover the CPU-based things, so we'll not delve any further than this, unfortunately. And the final section of today's this lecture is about applications in machine learning and how can we utilize today's knowledge and think about possible adaptation to your problem in machine learning. There are several of them. One can be, for example, any of you guys trained machine learning model before? Or just not yourself or your coworker or somebody you made some lecture? Okay, yeah, so pretty big number. You may see that some machine learning researchers, they don't really know what kind of model can be the best at the end. So they need to do a lot of experimentation before finalizing the prototype into the production or into the research, doesn't matter. So the core thing is they need to do a lot of experimentation and they need to have different configurations of your models and try one by one to see the result. You can one can attack this problem in a multiprocessing way, or it doesn't have to be multiprocessing API from Python. It can be any other API, external API from PyTorch, TensorFlow, or any other framework. But the idea is that you can spread each model training into separate job, into separate process, and then train independently, train in a parallel fashion, so that your result can be quicker, final result can obtain quicker, and instead of waiting your 3 models for 3 days, you can spend only 1 day and get your model, get your result and choose which one performs appropriately for your case. For example, in a more detail, let's say our machine learning simple neural network has 3 layers, a few neurons, 512 neurons, and learning rate like this. And second configuration has 4 layers with 256 neurons, and third configuration has 3 layers with 256 neurons. And we want to check every one, and then we put every model to a separate job, and then we will get score finally. This can be one application. Another application can be, if you guys have heard about validating models, there are different kind of techniques. One of the popular ones is cross-validation, 5-fold, 10-fold. It's basically if you want to prove your model performs same no matter how you split your data, your train test data and your train data and test data, and you should check every split one by one. For example, first iteration we take the first 80% for training, 20% for test, and then in the next split you split this way, this way, this way. So, and then instead of going every iteration one by one in a serial way, you can put your every split based pipeline into a separate process or job, and then you can also train and validate in a parallel way. And and the third one, also quite common, is let's say we have our complicated machine learning pipeline, and then we can kind of manipulate. But we have a complex pipeline, but we also have powerful compute. How can we efficiently utilize our powerful compute to the complex pipeline? So 2 common pathways here is using data parallelism and model parallelism. What's the difference? If we check the first one, data parallelism, let's say we have the your training data, right? And we can split your training data to we can split our data and train on the common model. So each split of your data can go to a separate process or separate job, and then this way it can be much faster compared if you do it like compared to like on a single one. And also like if you, for example, your GPU compute is let's say you cannot fit all the data to your one GPU, but you have several small GPUs. Then the way how you can split every part of your data into a separate GPU, and every GPU will work with only piece of data, and then they will combine as a result, like to the final model. Similarly, like the other like trajectory here is to use model parallelism. Is when you have the shared data, like you don't split your actual training data originally, but you can split your model, like every piece of your model. The reason can be also similar. For example, if your compute cannot fit the big transformer or like big GPT model or something, then you can split it across several compute nodes, and then train like in a distributed fashion, and then like you can collect the result afterwards. Does this slide make sense? Okay. Yeah, and like unfortunately this is just the high level like overview how we can apply. There is no really like supported example to show it, but I'm sure like there are a lot of examples over the internet. You can, if you have interest to find, there are many of them. So to summarize today's session, we went over about some basics of multiprocessing, what's the concurrency, what's the parallelism, what's the thread, what's the process, what's the difference. We stepped into the multiprocessing API in Python, how to start the process, how to monitor it. We also showed how to share the memory between different processes, how to manipulate them, and also how to create a pool of processes, and depending on your like compute, scaling it, and also showed some how parallelization can be useful for machine learning applications. Yeah, that's basically it for today. And if you have any questions, let's talk now. you can ask now, and feel free to we can discuss more. And this is our like donation page. Like feel free to donate also. Yeah.
Can you show some example code and running it?
Yeah.
Also, we can't see.
Yeah, one more time, just. Can you see my screen?
Can you make it a little full screen? And then maybe Control plus a couple times? Getting old, I can see. Let's get
This is our repository, and then if you go to this folder, today's date, parallelization, there are like several pieces of Python scripts, and every one is basically the reference from the slides. For example, here, this one is called log2.py, and you can directly run it. Log2.py, and it's here. Then we go to yeah. So the good thing is here that you don't need to install any external package or any external library. So you can use your own like Python interpreter, which you already have, and then let's say we run let's see pull2, we copy this code and then paste it. Python. Yeah. Yeah. Similarly, you can write like this kind of things in your own machine and try it. If you have any questions or problems running this kind of scripts in your laptops, feel free to raise your hands. We can help you to go like this. Paste it. Yeah, this. Yeah. That's all.
Cool.
Thank you.
Any other questions? Cool. Thank you. I think I'm gonna hit stop streaming.